Recent videos have dealt a lot with circuit theory and reviews of radios currently on the market. As we saw in those, modern technology has produced remarkable multiband radios that are portable, small, lightweight, sensitive and selective, and don't need AC to run. In this episode, I thought it would be nice to look at an older radio, a Hallicrafters S-38E, which followed me home from a hamfest about a year ago. It's been sitting on the shelf since then, waiting to be examined. So, let's do that. The S-38E was produced between 1956 and 1951, and was the last in the S-38 series that Hallicrafters produced, and that series began production around 1946. This model's pretty clean. A lot of them that you see are not as clean as this. You can see it's got a nice shiny finish still, and it's pretty much built like a tank. It's not exactly lightweight. It's not at all portable. It runs on 120 volts AC, and it's got a metal cabinet. So one of the first things that we're going to do is we're going to test this and see if the chassis is hot, and we'll kind of look around and look at the dial a little bit more closely. So let's move this just a bit so that you can see what I'm going to do. So this is the back side of the radio. See, this is all the original board there. This is obviously not the original cable. And in particular, this cable, as you can probably see there, is polarized. Okay, here's the polarized blade right there. So this was advertised or claimed to be in working order. I have no doubt that it is. So I'm going to plug this in and turn it on. And as I said, the first thing that we're going to do is we're going to see if the chassis is hot. Because, oftentimes people claim that when there is a polarized plug that the chassis is never hot. And as I've said in previous videos, that is oftentimes not true. So let's see. Alright, so it's plugged in. And what I'm going to do is I'm going to touch one lead to the back of the chassis here. Right here next to this adjustment. I'm not sure what that adjustment is, but there's a piece of metal there. Let's just move around here and zoom in on the meter. Okay. And so I'm going to touch one side, one probe, to the back of the chassis first, and the other side of the probe to the handle of my Tektronix oscilloscope, which is grounded here on the bench. So there's contact with the radio, and there's contact with the grounded handle of the oscilloscope. And that is a hot chassis. It's 120 volts AC. Let's turn it on, which I just did, and do the same thing. And I have a very strong suspicion that the AC will be gone. So there I've touched it to the back, and there I've touched it to ground. Just turn that down a bit, and you see that we no longer have the voltage. Alright, and we'll see in just a few minutes, looking at the schematic, just why that is. This radio is not something that I would feel safe operating in its current state. So let's continue now examining this radio. I've unplugged it. Okay, see, it's unplugged. And let's just kind of look at it a little bit more closely and see what we got. So this is the original backboard. Note the Underwriters Laboratory listing. Humorous given the last comments. 30-watt power consumption. It's usually kind of run-of-the-mill. And just look at how nicely conditioned the bottom is in. The pasteboard is all intact. We see the original label on here with the factory stamp over it. This is an All-American 5 design. We have 35 and 50s 85, and then another 36 adds up to, what, 121 volts. So this should be absolutely compatible with modern line voltage. And what looked to be the original rubber feet grommets, rubber feet anyway, on this. You zero in on this, you can see how they are cracked. They're actually still fairly good shape. Let's turn this around a little bit so that it's facing us again. And let's look closer at the dial. I mean, I have to say I'm a sucker for a beautiful radio face, and this is a beautiful face of this radio. So we have a band spread knob, which controls what today we would probably call fine tuning. We have the volume and on-off switch. We have the band selector. So it's band 1 is the AM broadcast band. Band 2 is 1.75 megacycles. Megacycles per second, or hertz, megahertz, the modern term. Band 3 from 5 megahertz to, what, 14.5. And then band 4, which is, looks like 12 or 12.5 megahertz up through 30.5 megahertz. Let me zoom in a little bit on this dial because there are a couple features I just want to point out. So the first feature is on the kind of middle shortwave band, which would be band 3 of this radio. I just love how they've got frequencies marked of stations in different nations and different cities. So we have Cuba, we have New York, South Africa, London, Havana, Korea, and so on. That's got a pretty high cool factor, and you can imagine just how excited one might be in the late 50s, early 60s to get a shortwave radio that kind of promised that you could hear stations in all these different parts of the world. And the other thing I wanted to point out is, zoom out just a little bit here, are the two civil defense markers here and here. Let me just zoom in a little bit more on that. And those were on the AM broadcast band dial. And these are interesting. These are a way of dating radios, US-made radios. These symbols marked two different frequencies on the AM band, 640 kilohertz and 1240 kilohertz. And these were part of something called the CONELRAD program. CON for control, EL for electromagnetic, and RAD for radiation. So CONELRAD was the Control of Electromagnetic Radiation program. And this was the forerunner of the Emergency Broadcast System and what today in the US is called the Emergency Alerting System, EAS. CONELRAD ran from 1951 until 1963, and radios that were produced for the US markets in that time frame by law, or at least by regulation, had to have those two frequencies marked. Pretty chilling stuff. But on this radio, kind of adds to the cool factor, I have to say. So this radio is pretty clean. There's a little bit of dust and dirt here in the corners of the dial, but it's not too bad. And as we saw before, it certainly works. When I turned it on and had the volume up, you could hear parts of a radio program, which I quickly quenched. So what I want to do next is go through and see just how closely this has been aligned or how accurate the dial frequencies are. And I'm going to do that not with radio, but rather I'm going to do that with a modern digital function generator that is calibrated in frequency. So here we've got the radio turned back around, and I'm just going to turn the volume on. And I've got a piece of wire hung up here on the ceiling of the lab. Turn that down rather quickly. And so I've just got the antenna wire alligator clipped to a longer piece of wire there. Alright, so let's just tune this bit off any frequency. Alright. Actually, let's put it on a particular frequency. And so there it's set on the dial to 1300. Let me just move this around so that we see it a bit more squarely. Alright, remember the Conelrad symbol was at, what, 1240, and this is just pretty much on the nose at 1300. Okay. Now, have my little Siglent generator here. Let's just put a BNC on it, and I've got just this kind of cable here that dangles, and I'm just going to dangle that over the antenna wire so it's not electrically connected. And let's dial in 1300 kilohertz and make a modulation frequency of 400 hertz is the time-honored setting. Okay. And so we should see now, we should hear a tone, and we don't. So how badly miscalibrated is this dial? Well, let's tune it up and down. And what we see is that this tone now is coming in at 1.4 megahertz or 1400 kilohertz, not 1300. So that's not terribly well calibrated, this band. But let's just see if it's off by the same amount at a lower frequency. So let's go down to 800 there and change the Siglent to 800 kilohertz. So there's 800, and we don't hear anything. So if we go up 100 kilohertz, we should see that signal again if everything is symmetric. And you see that we pick up the 800 kilohertz signal at just a little over 850. So we've got some alignment to do. Let's just turn that down a bit. Just for giggles, let's go to band 2 and set it at 3 megahertz like that and see how far off we are. Okay, so there's 3 megahertz on the Siglent, and it's nowhere to be found. there is a very strong signal at 3.2 megahertz, so it's 200 kilohertz off there. And you know, we can do this to death, but let's just go to 10 megahertz. And is that actually a signal that I heard there?
Which we can live a life.
So there's a broadcast signal somewhere around 9.5 megahertz. It's a religious broadcaster. Oh, and there was another one. Another signal that just faded out. And there's that. So not bad in the basement on probably 6 feet of wire. But so I wonder if we can find WWV. That's not WWV, obviously. In fact, WWV is nowhere to be found. Well, let's just bring the signal up to 10 megahertz and see how badly it is off on this band. Obviously, what we're going to have to do is we're going to have to align this radio through all the bands, and that's probably not that difficult in this circuit. So there's 10 megahertz. Turn this up a bit. See if we can find the signal. And it's interesting that we happen to tune the signal in at somewhere over 10.5 megahertz, but it's right over the WWV dot. Okay. Well, what I want to do next is open this up and just kind of poke around inside. I don't think I'll do the alignment, at least in this video. But let's open it up and see what's inside, just to get an idea of what, if anything, has been done internally before we go about fixing anything that needs to be fixed. I've taken the back off of this radio, and you can see it's reasonably clean inside. Maybe just shine some light in here. You know, there's not anything that really jumps out at me as horrifying. The tubes actually have some dust on them. Probably hear my dog in the background saying that, agreeing with me that that's a good thing. Dusty tubes mean that nobody has been inside the radio and felt compelled to take them out and do things to them, so that's good. Let's take off the bottom part of the chassis and look at what's underneath. So here we go. And just pan up and down a bit. So the first thing that you kind of notice here is that there are an awful lot of these old plastic sealed, but probably paper nonetheless inside, capacitors. And I don't see, well, I see some kind of kludgy repairs. For example, this, bend that out a little bit there. You can see that someone's just clipped out that little coil and soldered in a new resistor. It doesn't look like it's that new of a resistor, actually. But nonetheless, someone has been in here and done some work. And the biggest thing that you notice is these 1, 2, 3, 4 47 microfarad 450 volt electrolytic capacitors that are, oh, I don't like what I see there. They're cable tied together, which is nice. The cable tie came off, so it wasn't effective. And you can't see it, but down in behind here, all the leads on the negative side of the caps are wound together and soldered, but they're just flapping in the breeze. And on the radio side right here, they're probably a centimeter or less away from the metallic chassis. So there's that. Okay. And just kind of take a step back here and looking at the wire. For the power supply. In fact, let's see. Yeah, none of them go straight to... Well, yeah, one of them does go to the power switch. But it's not the correct blade from the power that goes to the on-off switch. So there's some work to be done here. And my dog agrees. But the nice thing and the most important thing for the alignment is that these capacitors look like they're in very good shape. There's no, it doesn't look like there's moisture that's affecting them or anything like that. So it'll be easy to get into these when it's time to do the alignment. Oh, you know, I just saw something else I don't like. Zero in on that. So I see one of these, I think these are called bumblebee capacitors, that are frequently cracked and almost always leaky at this point in their advanced age. So yeah, we'll test it and see, but almost certainly we have to replace that as well. All right, but overall, you know, I don't see water damage or anything like that in here, and it looks like it's been kept in a clean environment. You know, I don't see telltale signs of someone spraying solvents indiscriminately and wiping it up and having residue left over. So, you know, there's that. Before wrapping this video up, just wanted to do a couple of additional things where I point out what we started with, which was when this is turned off but plugged in, the chassis, or at least part of the chassis, is at 120 volts AC. And you can go to the web and download the service manual for this radio. And if you have one of these, I encourage you to do so. But zoom in a little bit here and just describe why the chassis is hot. So here is the AC plug, and you can see that if this side is hot and this side is neutral, and this switch is open, so the set is turned off, what happens is this wire is hot, this wire is hot, all these filaments are hot, and it's tied directly to ground. So when this is off, you've got this point right here, which is chassis ground, at 120 volts. Now when the switch is closed, it's dropped down to ground potential, but as long as this is open, you have this being at 120 volts. Now, if this were neutral and this were hot, then we wouldn't have that case while the set was off. In other words, while this switch is open, the potential stops here. But as soon as this switch is closed, again, you see that you would have the chassis at 120 volts. So, this is interesting, and it's of course fixable. We've described how to fix this in previous videos and make it safer to operate. And there are numerous websites that describe this as well. I do want to point out, though, one interesting thing about this radio, Zoom out a little bit, that I didn't point out earlier. So let's set it up like this. And what I want to do is show how this metal chassis radio, chassis and case, is actually a metal case within a metal case. So these are rubber, right? These feet. There's a metallic screw in there, but under that screw, right there, you can probably just see, is a plastic, or maybe it's Teflon washer. It's an insulated washer. And then this right here is cardboard or pasteboard. It's an insulator that then is attached to the metal frame of the internal chassis. So that's true for all four of these feet. So it's this one, and you can probably see these insulators up here as well. So if, and only if, these are intact, these insulators, and the metallic screw isn't misaligned and making contact with the outer case, then, if all that's true, then this is insulated electrically from the internal and half of the time hot chassis. I wouldn't stake my life on that, especially if you're dragging something like this home from a hamfest or buying it from an online auction. So it's something that you really need to be aware of. All right, well, there you go. A late 1950s, early 1960s vintage Hallicrafters S-38E. It's in very nice shape. I'm going to clean this up, change a couple capacitors, rewire the power circuit so that this is unlikely to shock a user. Spiff up the glass, remove some dirt, straighten out this slightly crooked tuning dial bar, and then align it and see how this performs. I will probably do all that in a part 2 video to follow in the future, but I'll wrap this one up right here and now. Well, I hope you found this interesting. If so, please give it a thumbs up below. And as always, thank you for watching.